So I'm going to go through the slides and then I'm going to do it on Excel as well. So mostly we're going to focus on the Excel part. I'm just going to go through principal component analysis with you. And I have a few slides here that is going to help. Okay, now I need that people one so I can admit you guys. So can I there we go. Okay, found a way to see you guys, or a little bit of you guys. Okay, so we're going to do PCA. So PCA is principal component analysis, and it's similar to KNN, so that we're going to group variables together. But in this case, we don't have a predetermined grouping. So we're going to determine a group, and then we're going to group it. So it's a semi-trained semi-supervised machine learning model. So you don't give it everything at the very beginning. So you have all of your data, then it's going to see and get correlations between the different variables in your data. And then you're going to see, okay, what impact those variables will have at the end score. And then the variables that has the least amount of impact, those variables or those groups, we're going to let them fall away. Okay, so that's the whole reason why we're doing PCA or LDA. It's also a k-means clustering. So it's a similar concept for all three of those. We're making sure that we don't have too many variables that is just going to create noise. Okay, so we are going to have a few steps. So we're going to crack open this black box. So we're going to first standardize our data. And we're going to make a matrix, a correlation matrix, and we're going to use the covariance matrix. Then we're going to get eigenvectors or eigenvalues, and we're going to then use those eigenvectors and eigenvalues to determine a specific amount. Let me just mute everybody else except myself. Okay, yes, you guys can still hear me. Good. Okay, then we're going to use it, and then after that, you're not going to use it for Varimax or mapping yet. You can use it next year or in BDAN, but we're going to do step 1 to 4 basically. So we're going to get the standardization form, we're going to get the matrix, we're going to extract the eigenvectors, and we're going to get the retention or the select. Okay, so this is basically what we're going to do. We have raw data, we're going to standardize it, and I'm going to show you all of that on Excel as well. So we're going to standardize it. Oh no, this one is the wrong. Why? Okay, there was another formula here that apparently did not want to be here. Let me escape that formula that disappeared. Oh, there we go. Sorry. Just let me get this thing. Okay. It's the same type. It's the same formula. It's just that I have made it so that it is easier to understand. Instead of having the difference of x minus the average of x with multiplied with the x minus the average of x transpose. So this is the whole summation. So instead of giving you guys the shortened version, I went and pasted this one in. So that is your covariance matrix. So that's what we're going to do. We're going to create a covariance matrix. And from that covariance matrix, we're going to add a few more steps to get your the matrix that we're going to use to get your eigenvalues and eigenvectors, because your eigenvectors gives you the direction and the eigenvalues gives you the magnitude, so what impact it has. So the direction is it going to be positive impact or negative impact, and the eigenvalues It's going to give you the magnitude. So it's going to tell you, okay, this eigenvalue has a larger impact on the final model, and it's going to tell you, okay, the eigenvalue that's correlated with that variable, that is going to be an important one. Okay, so this is this is just extra that I'm going to add for you guys. So there is an eigenvalue system that you guys can go and play around with, but I'm going to show you how to do it step by step. After you have done all of this, you're going to get your component retention, and this is what you guys will be using in PDAN. So then you will get your elbow plot. You're going to see, okay, this is where it goes down very sharp. So this is the best component number to choose. So it's better to choose 2 components instead of 3, because with 2 components, there's still some very good eigenvalues. So the eigenvalues is still good. So it still has a bigger impact. The smaller it is, the less impact it has. Okay, and then why are we doing this? So we're doing this so that if you're going to plot it again, then we're going to plot it on a different axis. So you rotate it. We're not going to do it in SMAA. We're going to do it in PDAN, but this is why we're doing it, so that we have the results better represented on a graph. Okay, so then it is grouped better as well. So it's making the grouping better so that you can see which groups are relevant. Okay, so it's very important, because if you don't have the relevant grouping, you can have a grouping in there that is somewhere here very far away from your axis, and it has absolutely no impact. So it's a small grouping that has no impact on the end result or the end model that you're focusing on. So you're going to rather than lose that grouping or that section. So that's why we're using it, but we're not going to do that. I'm just showing you how we're going to use it. Okay, so this is your component analysis, and these are the steps we're going to use. So we are going to use the raw data matrix. We're going to use a small one, because otherwise it's going to be very complicated. We're going to standardize it, correlate it, get the correlation matrix. Then we're going to get the eigenvectors, and then we're not going to do the rotation, so that's visualization. We are just going to get the component scores. Okay, so that is what we are going to focus on. So now I'm going to show you here. Okay, so this is your PCA from scratch. I have made it so that it is basically in steps. So this is your steps, and you guys do not have it like this in your POE part 2. So, oh, it's not in POE part 2, sorry. Okay, so we have PCA, we have this matrix. So you have a feature, and each feature has a sample. And this is going to be rewritten here in a matrix of 3 by 3. So 3 columns, 3 rows. So what do we do first? We're first going to get the mean or the average. Going to get the average of each and every feature. Yes, Dominic?
Hi, Nadia.
Yes.
Can you hear me?
Yes, I can hear you.
Could you please put the Excel spreadsheet on the chat so that we can all follow along?
Yes, okay, I can do that.
Thank you.
No problem. So the Excel, the Excel spreadsheet, yes. Too many slides, too many. Okay. So going to, oh no. Why? Okay. Is everybody, do you have your WhatsApps open? I'm going to share it on WhatsApp since it doesn't want to share. Okay, so everybody should be able to see it on WhatsApp. Unfortunately, I did not upload this one to the a folder yet, but it will be uploaded, so I will still get there. Okay, so I hope you guys get it in WhatsApp at least. Okay, did you guys get it? Thumbs up, thumbs down. Is everybody on the WhatsApp group? At least. Okay, fantastic, because sometimes we do have these team glitches, unfortunately, but we still at least have the WhatsApp group to help us share everything. Okay, so then we're going to get the mean or the average of each feature. So you're going to get the average of each feature. So let's do that. Average, oh no, that doesn't work. Average of feature B and average of feature C. Okay. Then we're going to get the standard deviation, and I'm going to show you now. You can still use the standard dev one, or you can use the standard dev S because it's a sample. So it's a sample data. It's not a whole population. So you guys can use, wait, standard deviation S. Let me just copy that. Nope, that's not the idea. Let me just first finish this one. Yep. Then in this one I can just put that. That's the standard deviation S. And then we have standard deviation again. Yeah. And if you are uncertain, we're going to, let's do the standard deviation without the S. So standard deviation, and it's for feature A. Okay, and then we have standard deviation for B. And then for C as well. And you can see that it is basically similar. So I'm just going to go here and decrease the decimal points. So as you can see, if you use standard dev or standard deviation S, it's going to be the same. But if you guys used, there's a standard deviation P, standard deviation P. That one might differ. See, that one is different. So I would not recommend you guys using the standard deviation P because that's population. So this is the standard deviation for this sample. Okay, so don't use this one. I'm gonna whack and draw. Yes, that could work. Don't use that one. Okay, so let's go back. So then we have, why do we need this? Why do we need the standard deviation and the average, or the mean and the standard deviation? Because we're going to standardize the data. How do we standardize the data? We're going to get the feature, which is given, minus the mean, which is the average, divided by the standard deviation. Okay, so we're going to have equals to, in brackets, the feature itself, minus the mean given, we can lock that one in, F4, divided by the standard deviation. I can lock that one in F4 as well. Why? Because then I can just drag this one down and it will still give you the correct summation. Otherwise, you can just go and type it in. Okay. And then now we have feature B. Feature B is going to be in brackets. Or just let me make sure about one thing. Yes, I did close my brackets at the top. So it's important because otherwise the summation is incorrect. Okay, so we're going to have feature B and we're going to subtract the mean, lock it in F4, close the bracket, divided by the standard deviation, locking it in, F4, enter. We can drag and drop. How do I drag and drop? So if you go to the right hand corner, bottom corner of your block, your cursor will change from white to a black cursor. Going to click, hold it in, drag it down, and release. Okay, so that is how you can do that. If there were some people that have not been able to do that yet. Okay, so that is how we're going to get the standardized version. Okay, so we're standardizing our data. So for the PDAN students that are here, this is also a standardizing your data. It helps you to make sure that the data is clean and centered. So you're going to make sure your data is then more usable and it doesn't have a lot of outliers, because if you can see here, this matrix has it's from 2 to 16, which is quite a wide range. But in the second matrix that we created, it is basically between -1 and 1. So we're making sure that our data fits into a certain into the interval -1 to 1, so it's easier for the computer to see where the data point falls. Okay, so we're not changing it, we're just changing the perspective of our data. Okay, and then we can again get our averages. We can get our average, and this is for feature A. This time I'm just going to drag it sideways because it's just going to pick up and give our averages. Okay, and we have our standard deviation. Let's do the S one again. Okay, so this one will be 1. Okay, so that is good. Okay, so that means we have successfully standardized our data. The mean is centered around 0, and the standard deviation is basically 1, so it's a standard deviation of positive 1 or a negative 1. Okay, so it's between positive or negative 1, and there's one that falls just outside of it, but that is how the bell curve also falls. Then after we have standardized our data, we can now get our covariance or our covariance matrix. So our correlation covariance matrix. So I'm going to just add one more title. There we go. Covariance correlation. And then we have our covariance correlation matrix here at the bottom. Okay, so we're going to create that now. Let me just add a little. Nope, that wasn't the one I wanted to increase. There we go. Okay, so how do we get our covariance? We're going to get our covariance for A and A. So we're going to have equals to covariance. So covariance or covariance.s, not P. This is a S, not a P. Okay, covariance, and it's A and A, so it's going to be feature A, comma points, mine wants a comma point, feature A again. Okay, so that is correct. Then we have the covariance, so covariance S of feature A and feature B. Yeah, let me just check this one. I just used the covariance. Okay, so if I substitute it in, it's still going to give you the same. It's not giving me the same answer. Okay, so I want you guys to use the covariance and not the covariance S. There we go. Okay. And it's A and B. So it's 0.67 and 0.652. Okay. Then we're going to have the covariance. So covar, not the covariance S, since it seems this one is not the same. We have A and C. Then we have equals to the covariance of B and B. And we have the covariance of B and C. And we have the covariance of C and C. Okay, C and C. Okay, so this was the first step. Now I'm going to rewrite it. So I'm going to rewrite into a matrix form. So this is going to be our covariance matrix. This is our covariance matrix. Okay, so this is important. So we have now, I'm just going to say equals to A, or you can just type it out. So you have A and A is 0.67, B and B, B and A. So A and B and B and A is the same. So 0.52 and 0.52. Then we have A and C, A and C. So we have 0.52 and 0.52. B and B, we got 0.67. B and C is 0.67. And B and C, so 0.67. And then C and C is 0.67. Okay, so this is your covariance matrix. So if we look at the steps that we had, we have our correlation or our correlation covariance matrix. So this is the one we have now. So if we have that one, our next step is going to be our eigenvectors. Okay, so how are we going to get our eigenvectors? I'm going to use this and I'm going to plug it in basically here. So we're going to get our matrix. I'm going to copy it. So that's why I did not say equals to sign. Otherwise, it doesn't really copy very nicely. Okay, so this is our matrix. And this is our formula. So this is your eigenvalues. Your eigenvalues is this delta. So we have the determinant of A. This is your vector. This is A. A is equals to the correlation matrix. So your covariance matrix is A. Then you have your minus delta, which is your eigenvalues. Your delta is your eigenvalues. So that's delta is your eigenvalues. It's hard to copy it, this delta sometimes. Okay, here we go. Is your eigenvalues. And then if you have your delta, then you're going to substitute back in to get your eigenvectors. Okay, so we're going to look at this now. See, this one is not completely exactly the same, but we're going to substitute in the values that we have. So we have, it is 0.67 everywhere except for the top two spaces. 6.7, so that one is 5.2, that's 6.7, that is 6.7, that is 5.2, that is 5.2, and 5.2, that is 5.6.7. Yes, okay. So this is what you're going to calculate. You're going to calculate you're going to solve this. So you're going to have your determinant of your correlation matrix minus your delta multiplied by the identity matrix. So the identity matrix is basically just this this matrix with one along the diagonal. Okay, everything else is 0. So it's basically A and A is 1 and everything else is 0. B and B is 1 and C is 1. Okay, so that is how you can rewrite that. Okay, so this is how we're going to rewrite it, and we're going to get the determinant of it. So the determinant of it is going to be given to you. I'm just going to copy and paste this one over. That. Okay, I just need to. There we go. Okay, and I will redo this. Okay, so my A changed. This is the originals. The original is also different. So the original was this one. So this one was the original. And how do you get the determinant of the square matrix? So I'm going to basically do it over. Okay, so it's like I'm going to do all of those lovely little squiggles over. Okay, so how do you get the determinant of a square? So in this case, I will show it to you now. We're going to make sure that we have this one correct first. So I'm going to zoom in a bit. Okay, so we have it as 0.67 minus delta. Why? Because we have that this is matrix multiplication, subtraction, and addition, but we're just doing subtraction. So it's going to be 1 on 1. So you have 0.67 minus the one in the exact same position in the matrix that's been subtracted. Okay, so that is how we can get it's 0.67 minus delta. This one stays at 0.52 and this one is 0.52. Why? Because it's minus 0. So 0.52 minus 0 is still just 0.52. So we can see that basically everything stays the same except for the middle. So the middle diagonal, it is minus the lambda. Okay, so let me just make 6, 7, 6, 7, 6, 7, 5, 2. Okay, so now that we have our matrix, we're going to get the determinant of the square matrix. So we're going to get the determinant now of the matrix that we calculated. How do we get that? So I'm going to show you how. So you have your first value that you're going to have here. So you have your first value multiplied by what's left. So I'm going to have you have your first value, then you have this little square left. So that square is basically, there we go. So I now have a matrix of E, H, sorry, H, F, and I. Okay, so that, let's say this is your matrix that's left. And how do you get your matrix is going to be calculated by multiplying. So, oh, actually, it's already, okay. I can just go it here. So you have then your A multiplied by what's left. So this is your the matrix that is left. Okay, then it's minus B. So this formula stays the same. Okay, minus B. So you have B, and then we're going to see, okay, what's left around B? So we're going to have, okay, we can't have it on that row, and we can't have it on this row, and not on this row either. So we have D and G, and F and I. Okay, so D, G, F, I. So that's how we found that one. Then we have plus, so it's positive positive C. So this was our B. Okay, I'm going to, there we go. And then we have our C. So let's do C as pink. So then we have our C plus C multiplied by what's left. So let's see, we have C, so what's not in those columns, so it's this one. Okay, so what's not in the columns that's around it, we have it as D, G, and E and H. Okay, so now that we have plus C, we are going to look at how we calculate it. So how do you calculate it from here? So from here, you have it as, it's going to be, you're going to get this formula from this one, and you're going to do it as follows. You have E times I crossover, negative, so it's a minus F times H. Okay, and that stays the same for all of them. So D times I minus F times G. D times H minus E times G. Okay, so that is how you calculate it. Okay, so that is important. Why? Because we're going to use it now. So we're going to use all of those steps now. We're going to use it here. So we're going to rewrite it out. Okay, so let me, I did not rewrite it out here. So I'm going to take this, copy it, and I'm going to now go back to this side. And here at the bottom, I have done this. So mine just changed. So my delta in this case, it was these values. So it changed. Oh, goodness. 0.52, 0.52, 0.67, 0.67, 0.52, 0.52. Okay, so this is how we're going to do it. Okay, so let's see. We are going to look at it from the perspective of what we have just looked at. Okay, so let's have A first. So we have, oh, this is 0.52, 0.52, 0.67, 0.67, 0.52. So you guys can use this page and just add your own values into it, but at this stage, this is where you have to calculate it. So you're more than welcome to go and do it by hand, but I am going to show it to you on Excel. Why? Because it's very hard to write it on hand. Okay, especially while showing you guys it. So I don't have a pen that's connected to my laptop. So okay, so that is your delta. So this is basically everything that we have already looked at, but now we're going to see. Okay, so we have your 0.67, and then what's left. So what's left is this. So then we have your minus your B. So it is going to be minus 0.52. So it's B, so it's going to be 0.52, and it's going to be that one as well. So it's going to be substituted that. Then we have plus your C, so plus 0.52, and what is left is that section. Okay, so now we can see, okay, now we have to still rewrite it. So let's see, okay, we have these two values, let's make this color different. Let's make it pinkish. There we go. So we're going to multiply those together and then subtract those two from it. We're going to multiply those two together and then we're going to subtract the other two from it, and then we're going to multiply those two together. Okay, so let me now go and try and type it out. Okay, so I am going to,
Sorry, Nadia, can you please show us how you got, can you please show me how you got negative 0.52, please?
okay, so this is the formula. So it's the formula of you have your A and you have your A, so it's the first value of A minus the B. So it's minus the second value multiplied by the matrix that is left for B, plus your C multiplied by the matrix that is left. So this is a formula. So this is, it's not, that's why it's minus 0.52. Does that make sense?
Yes.
Okay. So it's your determinant of a square matrix formula. Okay, so that's why I also have this lovely colorful theme for you guys so that you guys can follow the colors at least, especially if you're going over it afterwards, so that you can follow all of the colors. As you can see, I'm color coding everything. So let me just make it the correct color. There we go. I'm color coding everything for everybody to be able to follow. Okay, so let's look at the next step. So we're going to have, it's very hard to get this delta. Okay, so we have our pink values first. So we're going to have it and make it pink. Okay, so we have our pink values and we are going to multiply it. So we're going to now multiply out this matrix. So this matrix is multiplied out by doing E times I. So it's this first value and the last value minus the second value and the second position value and the other second row column 1. Okay, it's very hard to explain it in the air, guys. Okay, so let's have it. Then we have 0.67 multiplied by minus lambda. So I'm going to put a block bracket here as well, because this is our first section, is multiplying those two together. Then we're going to subtract. In this case, it's 0.67 multiplied by 0.67. Okay, so where did I get this? This is this part. Okay, so this is the E times I minus the F times H. So this is how you get the determinant of a matrix. Okay, so that is our first values. So this is just our first section. So let's now do our second section. So it's a minus, and now we're going to go green. Okay, so it's minus 0.52 block brackets. So we're going to multiply first 0.52 times 0.67 minus lambda, subtracting the other two. So it's 0.67 minus 0.52. So 0.67 0.52. Okay, so now we have our second section. Okay, then we're going to add our last section, which is 0.52. So I'm not going to make it yellow, otherwise nobody's going to see it, so I'm going to make it red. Okay, block brackets, getting the equation 0.52 times 0.67, so 0.52 multiplied by your 0.67 minus lambda, subtracting our 0.67 minus lambda times 0.52. Okay, So I have 0.67 lambda and multiplied by 0.52. And this should still be very bright red. Okay. Okay, so do you guys understand what's happening here? So this is the formula, and we first had our A, our big A, that we have calculated. Now we're getting it into a format so that we can get our lambdas separate. Okay, so I see there's hands up. Let's say Setsu.
Hi, Nadia. Could you please go back to where we were before?
Yeah.
Yeah. Shouldn't the okay, no. No, sorry,
Yeah.
ma'am. Yeah, I think
No
one
problem.
of the yeah, the last numbers in red. Can you just double check that?
Okay, let me
0.52
double check.
multiplied by 0.67
So let me
without the
double
lambda.
check this one. Ah, thank you. You picked up on it. That is correct. Yes, that was incorrect. Well done. Otherwise, I would have done all of this over and it's like, what's happening? Well done for picking up that one. Was the same question for the other person? Okay, perfect. Thank you very much. See, it can become quite you can become a bit confused, so that's why I'm also doing it in color. So so that it is easier to just catch up. Okay, so what am I doing now? I am now going to get I'm going to solve the inside first. Okay, so let's solve the inside first. So it's 0.67. I'm just gonna, oh wait, this one was wrong. Okay, that one had a different, this one has a different matrix, so I can't use it. Okay, so it is going to require my calculator. Why? Because well, you can probably calculate here at the side as well, so equals to 0.67 multiplied by 0.67, so it is 0.448. Oh, no. Okay, so let's go and rewrite it. So we are rewriting the section. So first going to fill in this first brackets. Okay, so we are solving this first bracket, so it is 0.67 multiplied by 0.67, 0.4489. Then we have minus lambda times 0.67. So we have, so it's equals to negative 0.67, negative 0.67. So it's going to be, because it is minus, so let me just type it out, 0.67 lambda. So this is the one I need to copy. Lambda. This is the FOIL method, right? First, inner, first, outer, inner, and last, right? So you guys still remember the FOIL method. There we go, this two, and then the last two, minus lambda times minus lambda is a positive lambda squared. So it's going to be lambda squared. So that is lambda squared. I don't think I have lambda. Yeah, okay. Can I create it? Yes, I can do that. Can I not? No, I can't. Oh, I can't get it into a square. Okay, so that's just going to be, that's how I'm going to write my square. Okay, then we're going to do the exact same for the other side, and the other side is, luckily there's no lambdas in it, so it is just a minus 0.4489. Ah, okay, that what happened. No,
Can you please slow down a little bit, please, Nadia?
no, no, my mouse broke. Ah, my mouse broke. Oh, something wrong. Insert. What did I do wrong? Like I'm typing, but it's not typing. Okay. Oh, okay. I did something wrong. Let me quickly just try and fix it. Like, what did I press? What did I press? Does it end now? Nope, that is not it. That one? Oh, okay. So sorry about that. I broke it. So it was 0.67 minus lambda. Sorry, guys. I just broke my own keyboard. No, I didn't break it, but it feels that way. Okay. Sorry about that. So we have solved those that one. Okay, so let's just add a bracket around the first one, otherwise we will forget to multiply it incorrectly. Okay, so we have solved the first two brackets, then we're going to solve the next bracket. So it's minus 0.67 times 0.67. So we already have the answer for that. So that is 0.4489. Okay. Sorry for all of the confusion. Somewhere I clicked just something wrong with the control, and then my keyboard was against me. Okay, so now we have on this side, we have to get 0.6 to 0.25 0.52, sorry, multiplied by 0.67. So we have 0.52 multiplied by 0.67. So we have it as 0.1675 minus, in this case, it's 0.52 multiplied by the minus lambda. So it's 0.52 lambda. Okay, where did I lose you? Setsu and then Misha.
I'm getting 0.34. 34.
Sorry about that. I typed it the wrong way around. Thank you. Okay. Let me 3484. See, it's sometimes hard to keep track. Okay, this one was 0.67 times 52, and that one was not that one. So 0.52 multiplied by 0.67, so it is this one, but it is just the negative of it. Okay, so it is minus 0.3484. Okay, and then we have this last one. It is luckily this one we already calculated as 0.3484. This is, oh, this one has to, you have to be careful now. This one is where it's, where the error comes in. There's a minus in front. So first let's do inside of the bracket. So inside of the bracket, 0.67 multiplied by 0.52 is 0.3484, and 0.52 can just move it to this side, so it's minus 0.52, and then we have multiplied that one in, and then we have a negative sign in front, so we have to be careful. So let me just copy, paste it at the bottom. So we are going to look at this one. So we have a negative 0.3484, but a positive 0.52 lambda. Why? Because we multiplied the negative sign in, right? Okay. So this is one of the longer processes because it is time consuming. Okay. So now, why did all of my colors disappear? Oh, I like the colors. Okay. Where's all my colors? Let me just. There we go. Okay. Colors help sometimes. Okay. It is sometimes also just easier to write this one out. Okay, this one, then we can see for this one, we can remove the brackets inside because we don't have to simplify it further. For this one, the brackets can be removed inside as well. Okay, and then for this one, the bracket was removed. Okay. So now we can go and see, okay, we have 0.489 minus 0.489, so we can take those two out, right? Because they cancel each other out. On this side, oh, that's lucky. We also have one that cancels out. It doesn't always happen, guys. We're just luckier this time. And this time, this one also cancels out. Okay. Oh, this one is nice, guys. I like this one. This one isn't as hard as the others. Okay. Now we can just simplify it further. Okay, so I'm going to simplify the red and the green first before taking on this purple monster. So let's copy and paste it over. So we have negative 0.52 times negative 0.52 lambda. So it's 0.52 times 0.52. Don't let your hands go faster than your brain. Okay, so that one's going to be a positive. So it's going to be a positive 0.2704 lambda. Okay, still going to keep it green to keep it out of the way. And then 0.52, this one is luckily already positive, and it is 0.52 times 0.52. So it is the same value, 0.2704. Okay, then we can add those two together already before we calculate the rest. So we can just do that. So we have, let's just do this value multiplied by 2. Okay, so we have these two added together is 0.5408 lambda. Okay, and I'm going to change it to the color of orange. I don't know. Which color should I change it to? Blue. Let's go with blue because that's the color we haven't used yet. Let's do blue. Okay, so we have simplified all of the green and the red. So now we can simplify the other. No, don't do that. Okay. Okay, this can also be done in Symbolab with this so that you can see if it is correct. Okay. So it's still 0 equals to this value. So we're going to now calculate this one. So this one is where it can become tricky. Okay, so it's 0.67 multiplied by negative 0.67 lambda. So let's get this value. So 0.67, 0.67 times 0.67. We have this one already, don't we? It was this one. Yes. Okay, so we have, it's just that it's minus, so it is 0.4489. And this is just for this one. Okay, so we're working with the one first, and then we'll work with the other one. So we're multiplying it into each and every one. So it is 0.67 lambda, so it's going to be 0.4489 minus 0.4489 lambda. Then we have it as 0.67 plus lambda squared, so 0.67 lambda squared. Then we're going to have subtracting, so we're now working with the minus lambda. So we're going to have minus lambda times 0.67 lambda, so it's going to be positive 0.67 lambda squared. Okay, so it's going to be lambda squared. Okay, so we're now working with this lambda. Okay, then it's going to be minus 0.67. Wait, is this one? Oh, I didn't simplify this one. Did I? No, I didn't. I didn't simplify this one. Why didn't I simplify this one? It is, why didn't I do that? Okay, let's just simplify quickly. 1.34. So this one is minus 1.34. That makes it easier, right? 1.34. This makes it a lot easier. Why didn't I do this sooner? Okay. Okay. So sometimes we still make mistakes. Okay. But now I have to recalculate this. Okay. So I just need to recalculate this one. So it is now it's equals to 0.67 multiplied by 1.34. So it is equals to zero, and it is a positive and a negative, so it's a negative 0.8978 lambda. Okay, lambda stays the same, lambda plus, okay, 0.67 lambda squared. Then we have this one now is going to change to minus times minus, so it's positive 1.34 lambda squared. And then we have a negative lambda to the power of 3, and that is correct. We need that power of 3. Okay, and then that is how we calculate this one. Okay, so now we have we can now just make sure that we combine these two. Why? Because they're both lambda squared. So let's add them together. So it's going to be 0.67 plus 1.34. Just say equals to as well. Okay, so it is equals to 2.01 lambda squared. Okay, so now we can just rewrite it out. And we're going to rewrite it as minus lambda squared, lambda to the power of 3 plus the lambda squared. Then we have negative lambda, and we have, oh, this one is also lambda. So we're going to combine those two. So it is equals to 0.5408 minus 0.8978. Wait, 78. It didn't give 0.98978. Okay, so that one simplifies to negative 0.357. Okay, so, and there is no other values, so this is going to be your total in the end. And then you guys can solve. Okay, so you solve for your lambdas, but I'm going to let you guys solve your lambdas in Symbolab. So this is where you can use it. So I want you guys to be able to get your this part at least. Okay, then I'm going to put it into Symbolab. There we go. It's quite easy to do that, and you just say enter to get your answer. So you can also go and simplify it on your own as well. So first you take out the lambdas, then you have lambda squared left, then you can do factorization to get your lambdas on its own. Okay, so you're going to have lambda as, yes, Bianca?
Sorry, Nadia. Just one quick question. I'm not sure if there's a mistake somewhere, but I tried to solve this on a eigenvector and eigenvalue calculator. And
There might be.
yeah, so we are actually working with, I don't know what you call it in English, but imaginaire.
Oh, imaginary values.
Yeah. So the one value that's correct, the one, well, I calculated with my, well, by hand, and I got one value for lambda is 1.695, but then the other two values
these lambdas are incorrect.
Yeah, and you can't calculate the other lambdas because of that imaginaire part of the thing.
The imaginary.
Yeah, so the
No.
negative
Okay,
root.
so I might have definitely then somewhere messed it up.
So this is my, I will drop the quadratic equation in the chat. And then we can maybe, I don't know, I did try to find the mistake, but I don't know where it is.
Okay, here there is a few websites here as well that I have. It's the matrix, the eigenvalue vector matrix. And there's also a cubic equation. So those are the two that you can use. So this one is the well, it should be. It doesn't look like it's working. Okay. Should be an eigenvalues and eigenvectors calculator. If the internet works. Thank you very much for picking up on that, because it does happen. Somewhere you just make one small mistake and then everything just is ruined. Okay, so let me just check this one. These are, so I just use it as a baseline to do the calculations, but I changed the values inside of my first equation, so that's why it's different. Okay, so let's paste it. In this case, it's 0.67, 0.52. So you guys can also do this. I just want you guys to be able to do the other one as well, because they ask you, or they asked them last year to be able to write it out. So 67, 0.67, 0.67, 0.67. Yeah, no. 0.67. Okay, then we can calculate it. And I see somewhere.
Yeah, that's correct. That's the one I also have.
Okay.
And then if you calculate it on the long method for the quadratic formula, you also have to use the quadratic formula, and then you get the negative root values.
Yeah. Okay. Yes. Otherwise, the Symbolab one is also fantastic. So it's just have to type it in correctly. You can use your matrix. It's a 3 by 3 matrix and a 0.67, 0.67, 0.67, and it's minus lambda in this case. So minus, where is the lambda? There we go. So you can actually put it in here as well, which is very nice. And I think I will also go and see what they did with the final paper for this subject, because I would rather have you guys actually use these tools than to do it by hand, because it's going to, in any case, give you, want the determinant equals 0. This one should also give you the answer and steps, which is what I like, but I don't. Oh, okay. It doesn't want to. Okay. Okay, so that one doesn't really work. But the eigen values, when you get that cubed expression, then you can go and substitute it in here. I think I definitely made a mistake somewhere. But let's try, see if it is correct or not. So we have our A, so our lambda, we have it as -1.
Sorry,
B
Nadia, the
is
recording
Nadia.
2
stopped.
point. What? Why did it stop?
The recording stopped.
Who stopped the recording? Was it maybe an error? When did the recording stop?
On my side, it's still showing as being recorded.
Yes, mine as well. Mine still shows it's recording.
My side, it shows that it's not recording.
Okay, mine shows it's recording and it started recording at 3 minutes past 6. So it should still record. Is that the correct correct one? Okay, where did mine go wrong? Okay, let's it looks better than mine. Okay, mine still says recording though, guys, so I'm hoping it's still recording. Otherwise, we'll make a plan. Okay, one shared. So let's do this. Bianca's one might be correct.
Sorry, Nadia.
Okay, yes.
Is there a constant value for lambda?
No,
There
no,
isn't.
we're calculating the lambdas now.
Oh, okay.
Yeah, so we're calculating the lambdas. So in the end, you're going to get your lambda values. And I knew one is going to be 0 in this case. Let me just calculate, put my answers in, and then let's see what's happening. So it is C is going to be negative 0. No, that should be correct. Yes, somewhere I did something wrong. I calculated something wrong somewhere. It was here. Okay, I calculated something wrong here. I can actually also just put this one in, so at least if you get here, that's already fantastic. So you can put that one in here, equals to 0. That whole equation equals to 0. then you get your lambdas as well. And it shows you here step by step. And I think my steps, what is your, there we go. So what's the steps here? Ah, okay, it blocked me. It's fine. Okay, so this value is incorrect. Those two are subtracted. So it is positive 0.52 times 0.52, 0.27. That is positive 0.27.
Sorry, Nadia, can you just show me, please, how you got negative 1.34?
Ah, okay. Negative 1.34. That was 0.67 times minus 0.67. So you're going to have 0. It was here on this one. It was 0.67. So it's minus 0.67 minus 0.67. So it's 0.67 times 2 basically. And it's just the negative of that to get that value, that part. Okay, let me see what else. I can, no, this one doesn't have that function. Strike through. There we go. It actually does have that. It's just harder to write. Okay. Okay. Oh, this is where it went wrong. This one got lost. That one got lost. Okay, now we know. Okay, now I know what happened. Okay, so it was.
Nadia, didn't that cancel out with the first?
Oh yeah, I did cancel out with the first. That's true. Ah, well done on picking that up. So that one was not the problem. That's not the problem. Okay, so that one, let's do a strike through. And that one is a strike through as well. Okay, so that was not the problem. 0.67. So that one is also correct. Positive plus positive. And then we had 0.67 times minus 1.34. I think it's this one. Zero 0.8979. Positive 0.67 squared. Then it's going to be minus lambda, minus, that's correct, minus lambda, so that is also correct. So what happened is this one. So 0.548. What's this value? Ah, okay. I don't know where it went wrong. Okay. We'll have to see what happened there. Okay, but you guys can also use this Symbolab for that one then. Just don't know where the, oh, it could be rounding errors. Okay, but let's see this one. If I add, this one doesn't have that step, right? Oh, there we go. That could be it. There we go. Oh, it is. Okay, there we go. So it is, well, That is a bit different, but it is squared. That doesn't look correct. Okay, I'm gonna put this one in there in any case, just see. Yeah, but we have a 0. We have a 1.81. Let's see. Okay, so we have 0, definitely. So the answer of 0, I did get an answer for mine. We have this one says it is this value. And let's just see, this one is 0.81. So we're going to see if it has the same values. Okay, then we're going to look at this one. This one's values were, oh great, it's in this format. Can you guess? So this one is 0 and it's 1.813. That's also correct. And 0. Okay, so that one is also gave me the correct answer, so mine was correct. And then you can use Symbolabs as well. So for your this solution, there we go. So we have 0, 0.969, okay, and we have 1.813. Okay, so this is correct. That one is correct. Okay, I did get this one correct. Okay, so remember we changed the values at the very beginning. So these values did change. So I'm just changing them again. 0.67, 0.67. Okay, and then you're going to, there's another method as well that you can use, but you can then get your lambdas. Okay, now if you have your lambdas, you can get your eigenvectors by substituting it back in here at the top, so into this one. So now you're going to substitute in your lambda value that you have calculated, and then you can solve it. Okay, so there's a row echelon form for solving it. Otherwise, there is, you have, so the row echelon forms, okay, that's not, there we go. So it's just minus 0. So it's going to be, you're going to have it as equals minus 0. There's just minus 0. Okay, then we're going to use row echelon form. So row echelon form is basically when you're going to see two rows, well, these two rows are exactly the same. So you're going to have row 1 that stays the same. And we have that rows 2 and 3, you're going to subtract it from each other. So I did put a few YouTube links here as well for row echelon form. And then you can say, okay, it's going to be equals to, oh no. This is going to be equals to 1. So you're going to have x1, x2, and x3, and it's equals to, and it is equals to 0. So you're going to have 0.67 multiplied, well, basically, so it's x1. So this is not multiplied by 1, this is x1 times x1. We have, in this case, 0.52 multiplied by x2. and 0.52 multiplied by x3 is equals to 0. And then you can calculate. So we can have that if x1 is 0, then you're going to calculate x2 and x3. And this is the part where it becomes complicated and where I will let you use the vector solutions. So in this case, back to this vector solutions, you can then go and get the eigenvectors. So for each and every eigenvalue, there's an eigenvector. So if your eigenvector was 0, you have it as 0, minus 1, and 1. So the row echelon form, I will go and fight for you guys so that you don't have to do that one. 0, minus 1, and 1. So 0, minus 1, and 1. And that is for your eigenvalue with 1. Then we have your eigenvector, eigenvalue of 0.969, and it is that your eigenvector is minus 0.192. So let's use that value. And it is calculating 1 and 1, 1 and 1. And then you have your last eigenvector, so 1813, 1. So you're rounding it off. 1. And your vector is 0.9098, so 0. Let's 9891. So if we round it off, 0.9098, and then we have the rest of the values is 1 and 1, 1 and 1. Okay, so this is your vectors and your eigenvalues that you are going to that you calculated. So the row echelon form, you guys are more than welcome to go and use that. Otherwise, you can use this. So this one is completely different because this one had a different value. So you can't use this one, but this one was calculated using the eigenvectors website, which is apparently not in existence anymore, which is very sad. But yes. Okay, so now that you have your eigenvalues and eigenvectors, you are going to use your standardized data. So this is the data that you have previously calculated. This is this one. So you're going to fill up this space with those values, and you're going to now multiply it with your eigenvector matrix, and you're going to get your principal component. Okay, so you're going to have the first, I'm going to just clear all of this. Let me just clear all of this. Okay, so you're going to have equals to your first, sorry, in brackets, feature 1A. So you have your feature 1A, sample 1, multiplied by your vector 1, 1, plus, okay, brackets, plus in brackets, we have the second one multiplied by the second value, feature A, vector A, plus times vector. Oh wait, I've substituted. Oh, okay. There we go. Okay. This one is then for feature 1. No, this is incorrect. This one should be. Why am I doing this? Vector 1, correct. Sample 1. See, this is where you make sure that it's correct. There we go. Okay, now that is correct this time. This one is incorrect because why? Is it too short? No, that's not it. Okay, so I'll just do it over for that one. Okay, and that is for vector 1. So you can keep that vector 1 when we're going to do it for each and every sample. Just making sure all of them are there. Yes, okay. And then we can do it for vector 2. So we have vector 2 and we have it as feature 1 multiplied by vector 1 plus feature B multiplied by this second value in vector 2 plus feature C multiplied by the third value in the vector. And why doesn't it give me a value?
The formula is saying feature A1 times vector 1 1.
We are using a point
You're
instead
using
of a
vector
comma.
2.
That's for each and every principle. Sorry. So this formula is just for the first one, and then we're using vector 2 for the principal component for number 2. So this is vector 2. So that one is just for the first one that I showed you guys, so that it is the formula that is shown. Just at least for the first column. The second column is then all of the features with vector 2. Okay. And then PC3 is vector 3's one. So then it's just the vector that you're using that changes. But why doesn't it give me...
Nadia, isn't it because we have 2.198 instead of 2.198? So the format's not the same for both matrices. So you see in AD8.
Oh, yes, that is true. Thank you for picking that up. This one is... That one is minus 2.198. That is correct, yes. And it's 0.9098. Okay. Thank you very much for picking up that one, because that is why it didn't work. Okay, so now it works. Okay. A comma and a point can ruin everything. Okay, thank you very much for picking that one up. So now we have the second sample multiplied by this vector, and we're busy with vector 2. So it is the exact same formula as for the first one. It's just that we're using vector 2 now. So it is feature B multiplied by the second value in vector 2 plus feature C multiplied by the third value in vector 2. Enter. Then we have sample 3 multiplied by first value plus feature B for sample 2 by the second plus feature C multiplied by the third value. There we go. Okay. And then we have the last one to do still. Okay, so it is feature 1 multiplied by the first value in the vector plus feature B multiplied by the second value in the vector. So this is basically vector multiplication, guys. I can also share an extra video with you on how vector multiplication works and why I'm doing it like this. Okay, then we have feature sample 2. B multiplied by that one. Oh. No, that was not the point. Plus feature C multiplied by the third value. Okay, one more to go. And then you can calculate the variance. Okay, so the variance is going to show you how it influences the model. Okay. I don't even know what time it is anymore, guys. What time is it? We still have time, or am I going way over time?
It's 8:05.
Oh, okay. Going over time. Almost done, guys. Almost done. Okay. There we go. So now you have your principal components. You get your variance of your principal components, and then you're going to say what influence it has then on your model. Okay, I'm going to add more extra content, extra slides, and this one is incorrect. I'm going to remove that one. I will share this Excel sheet with you as well. So let's do that. Okay, that's so that everything is here. Okay. Okay, so this is the row echelon form actually. I'm gonna keep it for you guys. This is how you can then, if you have your eigenvalues, sorry, it's my handwriting, but if you have your eigenvalues, then you're going to substitute it back in, and then you're going to calculate it. So this is how you can get your x's, so that you're going to put into your vectors. Okay, so I did share this with you guys. Otherwise, I have also added YouTube videos on how to do that. So that's after this step. So after you have gotten your eigen values, then you can go and calculate your eigenvectors using the row echelon form. Okay, I'm going to save this and I'm going to send it again to you guys. Are you guys okay? Yes, Bianca.
Yeah, Nadia, just 2 questions. And it's not 8:30, so can I please ask it?
Yeah.
The one question is regarding the eigenvalue. So the values we just calculated, is that where we just assume our equation is correct?
That's why I also give you the website so that you can like cross-reference yourself as well. So if it is incorrect, then you can go back and check. And in this case, mine was correct, but somewhere along the line, I felt like there was a problem. But there was a very nice eigenvectors calculation, but I'm not sure why. Oh, there we go. There we go. That's the one I was looking for. Why I thought it went out of existence. Apparently not. It is this one. It also gives you a very nice explanation as well. This was not a transpose though. There we go. This is the one I want. So this is, you can check yourself as well. So this is how you can check yourself and make sure you have the correct
Can you please just type in the values again? Because I did type it into this website and I don't get the same Landau values.
Okay. Yeah, no, let me do that as well, because sometimes We do 0.67, 0.67, 67. Okay. I want details. Okay, let me type this one in to this one. Ah, okay. Can you also type it into this this value, because are you sure it's 0.52 and not 0.53? Just make sure of that. Because if it's 0.53, it will have a different answer.
Yeah, I use 0.53.
Yeah, then it will have a different answer. So if you had 0.53, then yes, then it did have a different answer. Okay, so it was 0.52, not 0.53. Okay, so that's where it comes in. You have to be specific. Okay. So 0.52, not 0.53. Okay. So if it was 0.53, you would have the correct answer. Okay. So this one also gives you, yeah, all of your eigenvalues and your eigenvectors. And you can just use this as well then to make sure it is correct. Okay, so if you go to details and go down, then at least you can find this one or this here, this value. So this is where you're going to find if it is correct. Okay. And then your eigenvalues are there. It also shows you how to calculate and do your row echelon form. So I'm going to also see if we can just use this website instead of having you guys do this by hand, because that is just tedious sometimes. But let's see what the head of this module says. Okay. So that was, okay, so we still have time. Anybody else have questions, concerns? Yes, Bianca.
Yeah, sorry, last one from our side. Thank you
No
for that,
problem.
Nadia. And then can you quickly go to the last step, please, where we multiplied the last step, please, where we multiplied
okay.
the two.
Yes. So the last step?
Yeah,
Yeah.
just in the third column, the second row, just we're gonna see, why did we calculate it with row 9 and not row 10?
Row 9. Wait, okay, so this is with, you're multiplying these two vectors with each other. So you're multiplying the first, this row with this column. So you're going to have the first value in this row, multiply the first value in this column. Then it's plus the second value in the row, multiplied by the second value in the column, and plus the third value in the row multiplied by the third value in the column. So this is matrix multiplication, and I am going to actually send you guys some resources on this, because this is operations with matrices. So I actually luckily have some slides on this as well. So let me just go over it with you as well. Okay, so this is slides from Gareth as well, but you guys should know him as well. Okay, so this is how you can use matrices. So we have matrices, sorry. that are similar. So we have a 2 by 2 matrix, and this is a 2 by 2 matrix. So if you multiply, and a 2 by 2 matrix is not the same as a 2 by 3. Okay, so the second one is, so it's rows by columns. So it is a 3 by 2, and this one is a 2 by 2. Okay, so how do we multiply it? Is this, well, this is first addition. So adding matrices is going to be the first value plus the first value. So it's the first row, first column, plus the first row, first column. So this is simple. It's 1 to 1. So it's the first row, first column, plus the first row, first column. The second column, first row, second column, first row that we add together. So that is how you added the matrices together. So it's a simple step. And then also subtraction is also the same. So it's similar, it's a 1 to 1. But if you multiply it, that is where it becomes different. So in this case, we have a 3 that's multiplied into a matrix. So you're going to multiply every single value inside of the matrix with that 3 to get the answer. But if you multiply 2 together, so here it is, this is a 3 by 2, and it also tells you. I'm just going to, I want to get to the multiplication because that is the one that we want to focus on. So this is the one you used with your, there we go. This is the one I wanted to see. Okay, so we're going to get the multiplication. So you're going to multiply the first column with the first row. So you're going to first do 1 multiplied by minus 3. Then it is 4 multiplied by minus 3, 5 multiplied by minus 3, plus in your second column here, we have your 3 multiplied by a negative 4. So it's your second column, so that you can get your first row. So you can see this is the first row. So you have 3 multiplied by minus 4. So it is usually going to be from left to right. So if you have minus 1, it's 3. So it's this row multiplied by this column. So you have minus 1 times minus 3. Then you have 3 times minus 4. So that is your first value. So that is the row multiplied by the column. And then you're going to use it for each and every one, but I'm just focusing on this one now because this is exactly what you use here. So you are going to multiply, just want to scroll, you multiply your feature, so your feature, your column, your row multiplied by the column. Okay, so you're multiplying each and every value in your row by each and value in your column. So it's row times column. So let's see if I can use this. So it is that value multiplied by that value multiplied by that value, and that value multiplied by that value. You're going to add it up together to get your first component. Okay, so that is how you can look at it. I hope that helps. Let me write it again, just to make sure. So you have your feature 1, your first row multiplied by your first value in your first column. So it's row times columns. So it's going to be those two multiplied together. We have green, so the second 2 multiplied together. Now we're going to add, and we're going to have our third value as well, so that we have one matrix. So this is basically this is the first matrix that you're looking at, or your vector. So what you did here was you had your features. So let's say we have your features here. And this case, it's going to be just going to calculate it again. There we go. And you're multiplying it with just one vector. Okay. So you're just multiplying it first with the one vector, just with the one vector. Okay. So you are multiplying basically just the whole standardized matrix with one vector to get your first principal component. So you are going to, in this case, so it's going to be value 1 multiplied, oh, no, that's value 1, multiplied by vector 1. Then you have value 2 multiplied by the second one in the vector. Then you have, nope, that was not, value 3 multiplied by the third value in the vector. Okay, so that is how you got that value. Okay, now this one is again vector. We have value 2, vector, value 3, and the value 3 in the vector. So this is how you calculate each and every one. But we just put it together. Oh, no, that one is incorrect. We just put it together into one calculation. So that is second value, this is third value multiplied by the, there we go. So this is basically what we did. So we have just multiplied, wait, what did I do? Oh, that's what I did. Yeah. So we have multiplied the whole standardized data set with the eigenvector to get our first principal component. And then we get the variance of that first principal component. And this is how you calculate it. So you get your variance of all of the values inside. Okay, so this is actually what we did. And you can go and then do it. You don't have to do it as we have done it here at the top. You can go and do it for each and every one. So this is, you can just rewrite it. Maybe that would be faster. Okay. 0.14 minus 0.73 and minus 0.441 minus 0.41 minus 0.73, that feels incorrect. 1.14, is it the correct one here? Yeah, it is correct. Okay. And then you can go and multiply it with your eigenvector that you have received here. Okay. So then you can just paste it and make sure your points are commas instead, otherwise it's going to break everything. So it's a comma, comma, there we go. Okay. So then you can go and do it for vector 2 as well. Okay, and let's see. Why does this one not want to be? Just doesn't want to be, does it? Minus 2198. There we go. Oh. 2, comma. There we go. Okay. That one just doesn't want to completely change. Okay. So then you have your principal component for number 2. And then let's see if we can copy and paste it to get your principal component for variable 3. Okay, and then we're going to change this one as well. Okay, there we go. We have, In this case, it's nice because it just copies it over. And it's already correct. Okay, so that is then how you get your 3 principal components. You basically multiply each row with each vector to get your new vector. Bianca, does that help?
Yeah, so then in the bigger matrix, the one above that, then the value in the third column, second line, let me just see, is this the one we calculated with the formulas?
Yes. So this
Yeah.
is the exact same. So if you go
Yeah.
and look at the top as well, you can see you have the same, or you should have the same answers.
Yeah,
You
great.
just sometimes have to go and check, especially when copying stuff, if it actually copies over correctly,
Thank
because
you so
that
much. I
is
understand.
usually where the problem lies. Okay, so I think this one, there we go, somewhere, that one, there we go. Now that one is correct, and that one is also incorrect. Okay, so now it's correct. Oh, this one also is incorrect. Okay. So that is then you're going to see this one is going to be the same if you copied it over correctly. So that's why you just have to check. Okay, so it's literally, you're multiplying a 3 by 3 matrix by with a 3 by 1 matrix. So this is a 3 by 3 and this is a 3 by 1. And since these two values, so this is a 3 and this is a 3, it can be multiplied. If these two values were different, then it could not be multiplied. But it's going to be, in the end, it's going to be the outside. So it's going to be a 3. Oh, what's happening there? 3 by 1 matrix. So if you see here, this one is a 3 by 1 matrix. Okay. But I will also share with you guys these slides because this is where it is explained as well. And I will upload this, or we will have a matrix, this matrix multiplication, a masterclass one of the Saturdays. And we will upload it as well. Okay. Everybody okay? Everybody still breathing? Well, the half of you that's left. Yes. Alizibwe?
Yes, hi Nadia. I had a question. I had two questions actually. So the first one was at the very, very, very beginning when we were still doing the mean and the standard deviations with everything.
Yes.
What if there is no identity matrix that forms like that 1001 that you know that pattern that forms? What if we don't get that? Is it wrong? Like in the very
This one.
beginning? Yeah, but the one on the
Oh,
right hand
this,
side.
this,
Yeah,
this.
that A B A C that's
It, oh, this, yeah. Now, if this will, you will get this, by getting the covariance of AA. So, this might differ because as you can see, the one that I shared with you guys had a completely different correlation because I had different values with that one. So if the values change, everything changes. So you can't just use exactly the same for eigenvalues and vectors, but that's why it's important to follow these steps. And this will be correct if you have done it correctly. So then you will get the means as 0 and the standard deviation as 1.
okay, so if they aren't zeros and ones, then it's
Then
not
you
gonna work.
can, yeah, for this one, for
Yeah,
this
for that
step,
one.
yes. Because I have also said it's making all features have the mean 0 and the standard deviation of 1. So this is your standardizing your data, you're scaling your data. Okay, so you're centering your data. So there's also a few notes along the way that you guys can also read extra on. I hope that
Okay.
helps.
Yeah, thank you. And the second question was for our assignment two. I'm not sure if this is in the question, but are we allowed to put the colors in as well before you mark it if there's colors?
Yes,
Okay.
yes, please. That's why I'm showing you the colors because it's as you can see, it's very easy to get confused. So working with colors helps. You can also write it out. So you're more than welcome to write it out and then type it, because it also helps sometimes to just write it out as well, especially with the lambda squares, because sometimes it's just easier to write it out actually. So that's why I had the row echelon form. I wrote it out. Otherwise, we would have been here for a few more hours. Um, so yes, you're more than welcome. Use the colors. It's fine. We're going to mark it with the colors. Okay,
Thank you.
and yeah, Chantel.
Hi, Nadia. Yeah, I just want to go to the end where we ended up with the variance for each of that principal component. So what does
Yes.
this mean and what do we do with that? So what was the goal of
So
all of these calculations now up to this
so the
stage?
variance, so the variance is going to tell you which one of the vectors is ideal or not. So it's going to I just need to search for that quickly. Uh, so it is, oh, where is my, I have a lot of tabs open, guys. So it's the proportion of the total variance explained by the component. So it's going to help you choose which one is going to be the one that you're going to, I'm not sharing my screen. So it's going to tell you which one is going to have a higher impact or more influence on your model in the end. So that is why you are doing your principal components. So you can see, okay, the first one and the second one had a lower variance. So they will be better. Oh,
So the lower variance is
yeah,
within that group. So the lower
yeah.
the
So
variance within the group, the better the feature is or the component that you're using.
you want, yes, sorry, wrong way around for me. The higher variance
Okay.
components. You want to retain the higher variance components. So
Between the, what does the high variance
um,
imply
let me,
and why is it
there we go.
better?
There we go. So you want the higher variance component because it has more of an impact on your data. So it's going to tell you, it's going to show you that the low variance does not really have a big impact. So you're going to reduce some of the features. So you're rather going to focus on your eigenvectors with the higher variance, especially later on in your PDAN machine learning. So this is just the steps showing you behind the scenes. Okay. So this is usually done before you create your model, so that you can know, okay, it's actually going to have an impact. So now you can see, okay, principal component one, which is uh, the eigenvector 1. It doesn't really have a good variance. It's not going to have a big impact. It's actually not going to have an impact. So it's rather focus on the other two variance or values, so that we have less noise. So this is also reducing noise and reducing computational power at the very end. So that is why we're looking at the variance as well. But I will also add more, especially on that variance. Thank you. I will just make a note to add more information from the
Thank you.
variance, so that when I'm uploading it to ARC for you guys. Thank you for that question. So that I did not have anything on that one uploaded yet. So thank you very much. Okay, That was Chantal. Thank you, Chantal. Thank you, Bianca. Thank you for everybody that's staying and ask very insightful questions. I hope this didn't scare you too much, and I will also get back to you on how we will do the eigenvalues and eigenvectors. Especially, I need to just talk to my module lead as well. Okay, so I hope you guys have a lovely evening further. And if you don't have any more questions, thank you very much for attending. And I'll see you guys Friday with a tutorial. And I think you guys have covered trees quite well. So let me go and see in the assignment 2 what you're struggling with, and we'll focus then on that for Friday's tutorial. Okay, awesome.
Nadia.
Thank you. Enjoy the rest of the evening, everybody.
Bye.
Bye.